available in the 1950s. Those of you who know a little bit about the X-ray diffraction will realize that after the Braggs determined the structure of sodium chloride in 1912, very few organic structures could in fact be determined in the years after that because of the problems of getting around the phase problem. The methodologies which we now use conventionally on all the diffractometers here, which are the direct methods, were to come only in the 1970s. And in fact, in the late 1970s was when they really became accepted. Although the methods themselves appeared in the literature in the 1950s and the 1960s. Computers were not really available, so there were very few crystal structures at that time. And Ramachandran's group used those crystal structures to I show you two pictures. This is a picture of 1955. That's Ramachandran there. Then, as a young man of 33 or thereabouts, and that's Gopinath Khatta, who also died a few years ago. And this was the Madras department. This was the Madras physics department. And it was only later that Ramachandran distanced himself from physics by calling this the Department of Biophysics and Crystallography. And by the time he appeared in Bangalore in the early 1970s, he had transformed the name of his department to the Molecular Biophysics Department, and one in which I've spent my entire career. Ramachandran then wrote about this many years later, about collagen, and he said how these things really happen, the alpha helix by Pauling in 1951, and the DNA structure in 1953, and he said that the helix era had really begun. He also wrote about how he came upon this problem. You know, when he was a very young man who went to Madras University as a professor. He had worked with C.V. Raman at the Indian Institute of Science as a PhD student, and obtained his PhD. And then he went abroad, as everybody had to do. He went to Cambridge. He didn't like Cambridge, and he in fact comments later that Cambridge was not as exciting scientific place as Raman's physics department in Bangalore. So he actually returned to Bangalore within a year to become an assistant professor in the Department of Physics at the age of 27 or thereabouts. And a couple of years later, Madras University began its physics department. It started a physics department. They offered the professorship of physics to Raman. And Raman at that time was well past 60. And so he said, look, I'm too old to start any physics department, but why don't you take Ramachandran? And so Ramachandran became a physics professor, head of the department at the age of 29. Now, of course, there's one danger in India. If you become a head of the department at the age of 29, then of course life changes for you forever after that. And I think this impacted him in many, many ways. He was looking for something to do. He'd already started X-ray diffraction in Bangalore. And he thought he would study a biological problem. And unlike the way we do things today, he looked around him for a problem. And J.D. Bernal came to Madras, and Bernal suggested that he look at collagen because nobody knew what it was all about. And that's how he started. And just next door was a Central Leather Research Institute. So very quickly he was able to get collagen from them. He originally began with collagen, which was available in the biochemistry department, but later on he went to the rat's tail tendon, which was available in the Central Leather Research Institute. So that's the view of collagen today. It's a rope composed of 3 chains, and you can look at it in color with today's computer graphics. But collagen molecules which are like this now assemble. This is how they assemble. Eventually they will form tendon. If you look at the length scale along this axis, you can see that we're going from the realm of molecules to the macroscopic biological structures that you see in tissue and tendon. And as we go across this length scale, what we are really crossing are the length scales of what today people call nanotechnology. So chemistry and biology sort of merge seamlessly in this length scale region where you begin to look at real structures. So here are the three helices of biology: Pauling alpha helix, the Watson and Crick double helix, and the Ramachandran helix of 1954. Pauling actually came to Madras and talked about collagen. And Pauling, of course, gave a number of wrong structures. He was right with the alpha helix, but he was completely wrong with the DNA structure that he actually published in the literature. Those of you who have, I don't know whether it's easy for you, but certainly in the old institutions, these journals are still available. If you go and look at the 1951 or 52 issue of the Journal of the American Chemical Society, you will find Pauling structure of DNA there in print. Pauling structure of DNA was marvelous. It had these chains with all the phosphate groups inside and all the bases outside, exactly like an inside-out Watson and Crick structure. Well, what was interesting is Pauling was probably the most important chemist of the 20th century, and he knew everything that was wrong about this structure, but nevertheless he proposed it. And this does happen sometimes. So he did say that in 1953, I contended that Curie and I together should be allowed 2 guesses on collagen. Because he said at one point, when he was giving a lecture on the stochastic method and the structure of proteins, that he said everybody should have an opportunity to guess the structure once. They can't have a second guess. But he said since he's proposed the rule, he should of course be the exception and have a second guess of the collagen structure. But this didn't quite happen because Ramachandran had made the structure. And this was in his presidential address to a conference held in Madras in 1967. Francis Crick, however, in his book, The Golden Helix, which he wrote many years later, actually wrote about DNA and collagen, where he actually said that why is the collagen structure not as glamorous? He said it's very important, but he just says that I think what needs to be emphasized about the discovery of the double helix is that the path to it was, scientifically speaking, fairly commonplace. What was important was not the way it was discovered, but the object discovered, the structure of DNA itself. And then he said, the basic fiber of collagen is made of 3 long chains. And he says, the characters were just as colorful and diverse, the facts were just as confused, and false solutions just as misleading. Competition and friendliness also played a part in the story, yet nobody has written even one book about the race for the triple helix. This is surely because in a very real sense, collagen is not as important a molecule as DNA. This he wrote long after, when he was in fact a very famous man towards the end of his career. This is true. What he says is in fact true. This was a very colorful story, but as far as scientific and technical challenges are concerned, the collagen structure was important. But Crick goes on to add, of course this depends to some extent what you consider important. Before Alex Rich and I worked quite by accident to collagen, we tended to be rather patronizing about it. After all, there's no collagen in the parks. In 1955, after we got interested in the molecule, we found ourselves saying, do you realize that 1/3 of all the protein in your body is collagen? But however you look at it, DNA is more important than collagen, more central to biology, and more significant for further research. So as I have said before, it is the molecule that has the glamour, not the scientists. This again is true, but it does turn out that this should give us some food for thought. In that, in the 1950s, in Madras University, which was certainly not as well outfitted as IISc is today, Ramachandran did work which was absolutely contemporary with the work that was going on in Cambridge of those days. And in fact, he was working on some of the most important scientific problems of the times. But now, in 2012, very good data has appeared because single crystal X-ray diffraction now allows you to solve the structures of very long pieces of molecules. And when this happens, he actually confirms that the Ramachandran structure is actually correct. And since I was editor of Current Science for many, many years, I like this. because when you look at those spots, there are some extra spots. Now, of course, when you're interpreting data, you interpret the data that you can, and you leave out the data that you can't interpret. And this is what everybody does. And that's what Ramachandran did. He says that in the paper by Ramachandran and Ambari, the existence of extra spots that conflict with the existence of a 20 Armstrong repeat, which is slowly based on a schematic illustration, is a matter of controversy. If he had interpreted these spots a little bit more, he could have resolved the problem directly from the photographs, instead of doing it the way he did. But in doing it the way he did, he found the Ramachandran map. And furthermore, he says even Ramachandran himself neglected these extra spots when he proposed his last triple helix model. And I rather like this, so I thought I would put this up here. The conclusions in this 2012 paper is the average molecular structure of collagen does not correspond to the prevailing rich-click model, but corresponds instead to a triple-stranded 7x2 helical model, which is in fact the Ramachandran model of those days. This is the paper which appeared in 1963, called The Stereochemistry of Polypeptide Chain Configurations, which led to the Ramachandran map. And on the next slide, I show you how these calculations were done. Because those of you who want to calculate the distance between 2 points know what the formula is. If you want to calculate the angle between straight lines and you know x1, y1, z1, x2, you know that, then you calculate, yeah. But if you have now one more like this, and you have 4 sets of x, y, z's, then you have to calculate the radical angle. And then you have to do it for, change the radical angle. So a lot of calculations. They were all done by my colleague of later years, but then as a young PhD student, C. Ramakrishnan. He did it with a calculator which I show you there, so they involved a lot of calculations. He also involved the fact that you can't make arithmetic errors when you are doing these calculations. So he's a very precise man, and this is the structure of the calculation that he, the map that he produced. But the wonderful thing about the famous Ramachandran paper in the Journal of Molecular Biology in 1963 is sometime in the 1990s, around 1990, I was producing a special section of Current Science, a special issue commemorating the Ramachandran map. And I wanted to reprint the Journal of Molecular Biology paper. When I looked at the Journal of Molecular Biology paper, I realized that 2 figures had been interchanged. That there were only 3 figures in the paper, but 2 of them had been interchanged. And the famous figure which shows the original Ramachandran map actually has the wrong legend below it. But nobody had ever pointed it out in the literature in all those years. So I went back and asked my colleague, Professor Ramakrishnan, who was by that time already a very senior person. Ramachandran had retired and was living close to the institute, and he wasn't too well, so he couldn't travel very much. I went and asked Ramakrishnan, can we now correct this and publish this in Current Science, that this is the corrected version? He said, no, don't do this, because the professor might get very angry. He hasn't noticed the mistake all these years. So let's leave it at that. So I respected his request and did not do anything. In the subsequent years also, I didn't find anybody actually point out this error. And so I think this taught me one thing. I think the most famous papers are never read by anybody. And I don't think anybody's actually read the Watson Crick paper. Certainly, nobody has read the original Ramachandran paper. They've read the subsequent papers which have come, in which this mistake obviously was not there. So this is what I've done. I've actually corrected it here. That's how this thing would have appeared in 1963. You see, this is how it should have been. Now I've corrected it in 2012, when I was asked to give a talk on the impending 50 years of the Ramachandran map. So between 63 and 2012, all we've done is interchange the legends of 2 of these figures. This is how it looked at the beginning, and slowly improved with time. And then you see it looks different because the conventions are different. Here you go from 0 to 360 degrees. After some time you go from 0 to minus 180 and plus 180. Because once everybody begins to use something, the international unions will set up a committee. And once the international unions set up a committee, the committee will now decide on a nomenclature scheme that everybody has to follow. And therefore, everything changed again in the 1970s. And this is what it looked like. But I wanted to show you a famous review. Confirmations of polypeptides and proteins, written by Ramachandran and Sir C.V. in Advances in Protein Chemistry, 1968. This is a review article which tells you everything that you want to know about polypeptide stereochemistry in excruciating detail. In 1988, that is 20 years after this review was written, I had a chance to spend a very short while at the University of California in San Francisco. So I was in the biophysics and biochemistry department, and since I had very little to do, I used to sit in the library. And this Advances in Protein Chemistry was right there, so I would pick it up and look at it. And then one thing I realized that is if you go down the Advances in Protein Chemistry series, the most dog-eared article in Advances in Protein Chemistry in all the volumes is the Ramachandran and Sir C.V. article. So this told me that generations of American graduate students had actually read this as part of their courses, and it was heavily marked, it was disfigured, which also told me that American graduate students are no better than Indian graduate students. And in those days, even in America, I think photocopying was somewhat restricted. You probably needed a supervisor's card or something in order to copy. But I'll tell you a little bit about Ramachandran's personality. There is a footnote in this article right at the beginning, which the editors have put in, which they say by the author's request, the publishers have left certain matters of usage and spelling in the form in which they wrote them. So there was no way you could get Ramachandran to change what he wrote. He usually wrote it correctly, but he might not have written it in the form that the American publishers would have liked. But he, of course, obviously refused to allow them to change anything. Said, if you change something, then I won't allow you to publish it. And therefore, I think they finally recognized the value of the article and gave it. This is the evolution of the Ramachandran map. Today, of course, students will see it as a Google image if you type it in. It looks more colorful. That's the picture that you had on the screen before. And this is a symposium in '67 at which Dorothy Hodgkin, Linus Pauling, that's Ramachandran, that's A.L. Modulia, the then Vice Chancellor of Madras University, who did for Madras University what Ashutosh Mukherjee did for Calcutta University in the earlier part of the century. In the post-independence era, he was probably the most enlightened Vice Chancellor to preside over the destiny of an Indian university. You could have also recognized that in Dorothy Hodgkin and Linus Pauling are probably two of the most distinguished structural biologists of the 20th century. And most of them were present in the 1960s simply because of the impact of Ramachandran's work. That is my colleague Ramakrishnan, as he exists today. He's aged probably another year since this photograph, but looks pretty much the same. And this is what he's doing. He's teaching students how to calculate diagonal angles by hand and also making them do assignments. This is what he did at IISc today. I got the slide from him and put his picture onto it. So maybe you might have him once to IISc Mohali. The only problem if you have him is that if he gives you an assignment, you will have to do it. And where is the Ramachandran map useful? This is the structure of a protein Rubisco, which was the incorrect model, which was published in the literature in 1988. There was a correct model of Rubisco, which was also published in the literature 86, 89. And you can see in a correct model, every residue in the protein will fall within the allowed regions of the Ramachandran map. In a wrong model, a large number of residues will lie outside the region of the Ramachandran map. Why do I show you this? Because I saw this paper called Errors in Three Dimensions in 1990. But I have saved this now and sort of put it onto a slide so that I will not forget. The wrong structure of Rubisco was in fact published in the literature. This is a very important protein in photosynthesis and so on. This is the ribulose bisphosphate oxidase, and this was published by David Eisenberg, who I quoted right at the beginning, who dismissed the Ramachandran map. Presumably, if he had understood the Ramachandran map's utility, he would not have made this mistake about a quarter of a century after the map had actually been published. So today it's very commonly used for correcting protein structures. You can look at many things which my colleague Ramakrishnan has helped us to do. You can look at the distribution of residues. You can analyze structures, very beautiful structures. Here, for example, is a structure which has been proposed for the Huntington's disease polyglutamine by Max Perutz in the last paper that we wrote before we died, where there is a completely water-filled nanotube, and this is what is called a beta helix. But if you can analyze these structures and by using the Ramachandran map to actually look at what regular conformations are actually repeated. Now I will quickly tell you in conclusion, why do I talk about this and why have I been interested in the Ramachandran map all these years? This is really because I've been interested in the problem of designing polypeptides from first principles, and when you design them from first principles, you would like to make residues occupy certain places in the Ramachandran map. Effectively, what you would like to do is to bias the conformational choice, and when you look at polypeptide folding, there are two issues that you confront. One is the kinetic problem, the other is the thermodynamic problem of the stability of the final folded structure, and the problem of nucleation, of how do structures actually nucleate along the polypeptide chain. And in all of this, the Ramachandran map proves to be very useful when you try and see how a structure is actually formed when you eventually bring all the phi psi or Ramachandran dihedral angles to a similar point in the Ramachandran map. So I will not bother you with this except to tell you that in analysis of folding, the map is very useful. In the design of peptidomimetics and conformationally constrained peptides, the Ramachandran map is extremely useful. For example, if you look at any protein, because you have a pyrimidine ring, the allowed regions of Ramachandran space are just that. If you invert it about the center of inversion, you get what is allowed for D protein. So now if you want to make something which folds in a particular way, you can in fact insert a D protein. And this is the kind of work that we do in generating structures in the laboratory and characterizing them experimentally after first principles design. But I will not worry you about what we do, except to tell you that you can use amino acids other than alpha amino acids. You can insert carbon atoms into the backbone. You can lengthen the backbone a little bit. When you do this, of course, what happens is you get more degrees of freedom. When you get more degrees of freedom, the Ramachandran stereochemical problem actually expands. You expand conformational space. And today, the foldamers or molecules which fold like biological polymers is a very active area of research where you can in fact get helical structures which are not conventionally encountered in proteins. So in fact you can use amino acids with additional degree atoms inserted in the backbone to mimic the kind of structures that you see in proteins. But this is a technical issue which I will not worry you too much about, except to tell you that if you introduce additional atoms, then of course you introduce additional dihedral angles and additional degrees of torsional freedom. And if you go to a gamma amino acid, for instance, you have 4 degrees of torsional freedom, whereas in proteins per residue, you have only 2 degrees of torsional freedom. So you can now look at ways of representing these structures and ways of designing these structures, but nothing that we do really goes in conceptually very much beyond the ideas which Ramachandran introduced into the literature many, many years ago. You can today generate helices with hydrogen bonds, bonded structures, which are not found in proteins, but are in fact found in that paper of Bragg, Kendrew and Perutz, in which all the hydrogen bonded structures were in fact not the structures that you find in protein. But you can today generate them in synthetic molecules quite well. So you can make new polypeptide helices, and the principles for making them are in fact really derived from the fundamental work which Ramachandran did. But I want to show you one thing which has emerged recently from work in my own laboratory. That is, if you take gamma amino acids, that is, you have a genetically coded alpha amino acid, you just put 2 more CH2 groups in the backbone, you lengthen it. So that's a gamma amino acid. Now you would imagine you have introduced more degrees of freedom, therefore this molecule must be more flexible. But it turns out that if you have introduced more atoms, the molecule actually becomes even better folded. So all the gamma amino acid containing molecules that we get are in fact folded. So how do you explain this? There are interesting ideas which float around in the literature, which I thought I would show you. This, for example, is a paper which appeared some time ago, written by one of my colleagues, Raman, a very distinguished theoretician. He wrote a paper on the organization of alkane chains in water and the length-dependent crossover from a helix to a toroid, what he called, all the theoreticians would like to use terms from biology. He used the word molten globule. Effectively, what it means is that if you have a long alkane chain, it won't stay long. After a certain time, it will start coiling back on itself. Subsequent to these papers which I saw from Raman's group, it turns out that there have been papers which have appeared, theoretical papers which have appeared in Angawati Chemie, where people ask this question: what is the last stable, fully extended alkane? So after you have about 17 or 20 carbon atoms all laid out, the chain begins to sort of fold back on itself. It does make some sense, because at some point or the other, conformational entropy will be overcome by collapse, giving rise to favorable van der Waals interaction. So folding may be a property not only of the alpha amino acids, but of other kinds of structures. Is the Ramachandran map useful in other ways? It turns out that if you go back and look at Pauline's original papers in 1951, and you look at the PNAS paper, it's very hard to tell the difference between a helix which goes this way and a helix which goes the other way, if you're not used to looking at them. It's difficult to tell a left-handed helix from a right-handed helix. The problem is actually a very complicated problem. If I hadn't told you that this was the left hand and this was the right, and you find it hard to tell, but you would be able to tell that. Maybe if you had both objects, you would be able to tell that one was approximately the mirror image of the other. Pauling, all the structures that he drew in his original papers had the wrong hand. They were all left-handed structures, where there are helices in proteins that are all right-handed structures. But Pauling